Probability is very similar to what you've done in set theory previously in your previous courses. So let me review set theory that is really relevant to probability theory. So first, a set. And I'm going to just use the naive set theory. So a set is a well-defined collection of objects. A universal set is the collection of all possible well-defined elements. We will usually denote U as the universal set. At least that's in set theory, we did that. The empty set is a set with no elements. And I'll usually denote it by this symbol here. I will use Venn diagrams, which are these graphical representations of sets and their operations. A subset. Oh, actually, I wonder if I probably have better pictures here. So let me look at the pictures in this. So this is a Venn diagram. Okay, so A is a subset of B if X in A implies that X is in B. So A is a subset of B if every element in the set A is also an element in the set B. So this set A is a subset of the set B if every element in A is in the set B. A is equal to B if A is a subset of B and if B is a subset of A. A is a proper subset of B if A is a subset of B and if A is not equal to B. So the set B contains at least one element that is not in A. A is always a subset of itself. The empty set is always a subset of any set A. The power set. The set of all subsets of a set A is called the power set of A, and it is denoted by 2 superscript A. The reason for this notation is that if we let n of A be the cardinality of A, the number of elements in the set A, then the cardinality of 2 to the A, meaning the cardinality of the power set, is 2 to the power, the cardinality of A. So it looks like a nice formula here if you use this notation for power set. Set operations. Union. A union B is a set of all X in A or X in B. Is a union of the sets A and B, which is the collection of all elements in either A or in B, or in both A and B. So let A be the set, let B be the set, then A union B is everything that's either in A or in B. And it could be in both A and B, that's fine. A intersect B is a set of all X, such that X is in A and X is in B. It is a collection of all elements that are in common with both A and B. So suppose this is set A and this is a set B. then A intersect B is this overlap. So it's the overlap between these two sets. Set difference. A take away B, sometimes denoted by A minus B, is the set of all X in A, such that X is not in B. So it's the set of all, well, let's see. So it would be the set here of all elements that are in A, but they're not in B. So it's all these white space here, these spaces to the left, that is in A, but it does not include any of this right half, right portion here, the portion that's shaded blue. So it's this. So this is A, take away B. The complement of A, denoted by A with the superscript of C, or with a bar above the A, or a minus in front of the A, or this little symbol not A, or writing out not A, or a little prime A. Or of course I forgot what that was. That was supposed to be a squiggle. Oh, the squiggle is here, but not showing there. Okay. It was there in the code, but not showing. I probably need a slash for it. Okay. It is U take away A. It's a set of all X in the universe, which are not in A. It's everything outside of A. Note that the complement of the universe is the empty set. The complement of the empty set is the universe. Everything that is not in A is, well, the universe without A. The number of elements, the cardinality of A, plus the cardinality of not A, is the cardinality of the universe. So the cardinality of not A is the cardinality of the universe minus the cardinality of A. Disjoint sets. Sets A and B are disjoint if A intersect B is the empty set. They have no elements in common. When we're talking about events in the next few minutes, then we'll usually call disjoint sets mutually exclusive events. Sometimes we call these mutually exclusive sets, but usually we'll call them disjoint sets. A sigma algebra. Let F be a collection of subsets of S, then F is a sigma algebra. If S is in this collection, F, and if the empty set is in the collection F, and if A is in the collection F, then so is its complement. And if a countable number of A sub I are in the set F, in the collection F, then the union of these A sub I's is also in the set F. So let F be sigma algebra, and let S, so let F be a sigma algebra of S, where S here we're going to be calling the sample space. Then I have the following probability axioms, Kolmogor's probability axioms. The probability of S is equal to 1. The probability of A is greater than or equal to 0. A here is any element in the sigma algebra F. 3, if A sub I is a countable collection of mutually exclusive events, mutually exclusive sets. So let's say if A sub I is a countable collection of disjoint sets, with A sub I being in the collection, then the probability of the union of A sub I is just equal to the sum the probability of A sub I. So first off, I want to show that if E sub 1 is a subset of E sub 2, which is a subset of S, then E sub 1 is less than or equal to then the probability of E sub 1 is less than or equal to the probability of E sub 2. So let's partition E sub 2 as follows. Since E sub 1 is a subset of E sub 2, then E sub 1 and E sub 2 take away E sub 1, so E sub 2 intersect not E sub 1, form a disjoint partition of E sub 2. So the guy in the middle, E sub 1, union E sub 2 intersect not E sub 1, so this green torus on the outside. Well, the union of these is E sub 2, and their intersection is the empty set. So these are a disjoint partition of E sub 2. So the probability of E sub 2 is equal to the probability of E1 union E2 intersect not E1. So, and that's because E1 union E2 intersect not E1 is E2. But since these are disjoint, then by the third probability axiom, this is equal to the probability of E1 plus the probability of E2 intersect not E1. But by the second probability axiom, this probability is always greater than or equal to 0. Therefore, the probability of E2 is greater than or equal to the probability of E sub 1. And that's what you want to show. Next, I want to show that the probability of the empty set is 0. Well, I'm going to show that the empty set, along with the empty set, give me a disjoint partition of the empty set. Well, the empty set union the empty set is the empty set. And the empty set intersect the empty set is the empty set. Therefore, the empty set, along with the empty set, give me a disjoint partition of the empty set. And so, the probability of the empty set is equal to the probability of the empty set union the empty set, since the empty set is equal to the empty set union the empty set. But since this is a disjoint partition, by the third of the Kolmogorov probability axiom, this probability of the empty set union the empty set is just equal to the probability of the empty set plus the probability of the empty set. Subtract the probability of the empty set from both sides of your equation. Therefore, the probability of the empty set is 0. And that's what you wanted to show. Let's show the next property. For all events A, I'm calling it an event. It doesn't really matter. For all sets A, I should call it a set. In the next few seconds, I'm going to say that sets are events. So, for all sets A, we have that the probability of A is always between 0 and 1. So given any set A, we have that A is a subset of S, because A is in F. And the empty set is a subset of A. That's due to the property that the empty set is a subset of all sets. Therefore, by this first property that we showed, the probability of the empty set is less than or equal to the probability of A, which is less than or equal to the probability of S. By the first Kolmogorof's axiom, probability of S is 1. By the previous property, the probability of the empty set is 0. Therefore, the probability of A is always between 0 and 1. Let's show the next property. This is going to be called the addition property for probabilities. So the addition rule. The probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. So this is going to be, actually, I think one of the sections of this chapter will be dealing with just this one property here. So let's show this. So first, if I look at A and if I look at B, intersect not A intersect B, meaning if I look here at A, and I look at B, take away A, then this becomes a disjoint partition of A union B. So A union B is equal to A union B intersect not A intersect B. And A intersect B intersect not A intersect B is, well, the empty set. Therefore, A and B intersect not A intersect B is a disjoint partition of A union B. And so the probability of A union B is the probability of A plus the probability of B intersect not A intersect B. So now let's look at B. And so B can be partitioned as follows: as A intersect B and as B intersect not A intersect B. So B is equal to B intersect not A intersect B union A intersect B. And so that's a partition, and it's disjoint because B intersect not A intersect B intersect A intersect B is the empty set. So there's no overlap between these two sets. Therefore, B intersect not A intersect B and A intersect B form a disjoint partition of the set B. So the probability, so by the third of the Kolmogorof's axioms, we have that the probability of B is the probability of B intersect not A intersect B plus the probability of A intersect B. Therefore, the probability of B intersect not A intersect B is just the probability of B minus the probability of A intersect B. Therefore, the probability of A union B, which we just found above here, to be the probability of A plus the probability of B intersect not A intersect B, is equal to, well, I just calculated this. The probability of B intersect not A intersect B, we found to be the probability of B minus the probability of A intersect B. Therefore, I've shown what I wanted to show. The probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. If A and B are disjoint, meaning that A intersect B is the empty set, then the probability of A intersect B is 0. Well, if A and B are disjoint, mutually exclusive, then the intersection between A and B is the empty set. Therefore, the probability of A intersect B is the probability of the empty set, but we already showed the probability of the empty set is 0. So I'm done. So, plugging that in here, we have that if A and B are disjoint, then the probability of A union B is the probability of A plus the probability of B minus this, but this term here is 0. And that's what I wanted to show. And so if A and B are disjoint, then the probability of A intersect B is 0. Therefore, by the previous property, the addition rule, the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B, which is 0. Therefore, I can disregard that last part. Therefore, this is equal to the probability of A plus probability of B. And that's what I wanted to show. The probability of not A is 1 minus the probability of A. Well, A intersect not A is the empty set, and A union not A is S. Therefore, A and not A is a disjoint partition of S. So 1 is the problem. So by the very first of the Kolmogorov axiom, the probability of S is equal to 1. But S is just equal to A union, not A. Since this is disjoint, so it's because S is a partition of those two sets. Since this is a disjoint partition, then by the third Kolmogorov axiom, this is equal to the probability of A plus the probability of not A. Subtract the probability of A from both sides of your equation. So the probability of not A is 1 minus the probability of A. So now let's translate. So now we're going to do some translation. So I'm just going to say, well, what you knew in set theory is now what you know in probability. So I'm going to translate from the concepts that you know from, first you started set theory was in grade 7. So, and you did this they always started off every book from grade 7 and above. The first chapter or two were always set theory. So what you did in grade 7, 8, 9, 10, 11, 12. Let's translate that into a new language, probability. So elements, members of a set, are now going to be called simple events. So these simple events are just members of your set. The universal set is now going to be called the sample space. Any subset of the universal set is called the event. The complement of a set is called the complement of an event. The union of sets is called the disjunction of events. It is the or of two events. So event E or event F. Well, of course, you can have two or more events. So it's this symbol here, the or. Intersection of events is just the conjunction of events. It's the and of events. It's this symbol of events. Difference of sets is just the difference of events. So let me give you, so that's the correspondence between our language of set theory and our language of probability theory. So let me give you these definitions without sort of the set theory behind it. So an event is a collection of results or outcomes of a procedure. A simple event is an outcome or an event that cannot be further broken down into simpler components. A compound event is an outcome that consists of more than one event. A sample space, S, consists of all possible simple events. So let's look at some examples. Suppose I have some of the following procedures, and I'll give you an example of an event and what its sample space is. So single birth. Well, you could have one girl. That's an event. The sample space is, well, boy, girl. Suppose you have the following procedure, 3 births. You can have, well, let's say 2 boys and 1 girl. So boy, boy, girl, boy, girl, boy, girl, boy, boy. So 2 boys and 1 girl. These are simple events. Sample space will consist of, well, boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. Those are the only possibilities you have for having 3 births. A random experiment. An experiment is called a random event if the result may be one of various possible outcomes. A trial. So each conductance of a random experiment is called a trial. A simulation is a procedure, usually on a computer or some other technology, of a process that behaves in the same way as the procedure itself so that the similar events are produced. Mutually exclusive events, which is the same as when we said disjoint sets. Now, of course, when talking about events, sometimes I call them disjoint events, even though that's supposed to be terminology for sets. But again, since set theory and probability theory are really the same thing, sometimes we just sort of use the same terminology for them. Okay, so two or more events are said to be mutually exclusive if the occurrence of one excludes the occurrence of the others in the same experiment. So say that this is event A and this is event B. There's no overlap. So these are mutually exclusive events. These are disjoint sets. Equally likely cases. So the outcomes are said to be equally likely or equally probable if each one has an equal chance of occurrence. So say you have a coin and it's a fair coin and you flip a coin, then, well, there are 2 outcomes if you flip it once, head, tail. So there are 2 outcomes. If you're assuming equally likely events, equally likely cases, if you're assuming that this coin is fair, that they haven't somehow given you a loaded, a fake trick coin, then the likelihood of, flipping it, getting head, flipping it and see, tail, should be the same. So it should be that you have a 50-50 chance of getting either of those 2 options. Now, and so you go, well, that's because, I flip, I have tail, and there are 2 choices, head, tail. So 1 out of the 2 is tail. So therefore, 1 out of 2, it's a 50-50, it's a 50% chance they get tail. Okay. Good. That's a good way of thinking about it. If, and only if, this is equally likely cases. So it turns out that if you have equally likely cases, then probability is really just counting. It really, it's really sort of a branch where we're really looking at, can you count? And so, can you count how many events occur doing this particular procedure over how many possible events there are? The number in event A divided by the number in the sample space. So you're just looking at the cardinality of these two different sets. Okay, so that's good, it's just counting. But not just because you have a certain number of events, you can't really figure out probability that way unless you assume equal likely cases. So let's suppose we have the following situation. You decide to climb up to the top of the Empire State Building and you jump off. There are two possible outcomes. You live or you die. Now, it is not just because there are two possible outcomes, that doesn't mean there's a 50-50 chance that you live. And so in this case, it's not a simple sort of counting procedure to determine the likelihood of those two events, of any one of those two events. And so in the next chapter, we'll be able to deal with situations like that. And it'll be very similar to what we're doing in this section. So once we get, well, this chapter, once we figure out what to do with this chapter, we can sort of combine results from this and previous chapters to actually be able to deal with all situations. So we first deal with this situation where I only have to look at counting. So I figure out everything just by counting. Then, after I've done that, I go to the more general case where I, can relax that. But it turns out that but as long as we know how to do this case, we can then easily do the general case. Okay, so subjective probabilities. P of A, the probability of an event, is found by simply estimating its value based on knowledge of relevant circumstances. So that's a subjective probability. A relative frequency probability. You conduct or you observe a procedure a large number of times, and you count the number of times that event A occurs. And so you estimate it as follows. The probability of A is the number of times that A occurs divided by the number of times the trial is repeated. So the classical approach to probability, which requires equally likely outcomes. Assume the given procedure has n different simple events, that each of those simple events has an equal chance of occurring. If event A can occur in S of these n ways, then the probability of A is S over n. It's the number of ways that A can occur divided by the number of different simple events, the size of your sample space. The law of large numbers says that these will approach each other. So as the procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. So von Mises's law of large numbers says, if an experiment is performed repeatedly under essentially homogeneous and identical conditions, then the limiting value of the ratio of the number of times the event occurs to the number of trials as the number of trials becomes infinitely large, approaches the probability of the occurrence of the event. It is assumed that the limit is finite and unique. So that's the law of large numbers. So let's do the following example. Assuming that boys and girls are equally likely, find the probability of getting 3 children of all the same gender. So when 3 children are born, the sample space is boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. And so, find the probability that all 3 children have the same gender. Oh, let's see. Boy, 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 same gender. Girl, 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 same gender. In all the other cases, well, they're not all the same gender. You have some boys and you have some girls. And so 2 out of the 8 cases have all 3 of them having the same gender. Therefore, the probability that 3 children will have the same gender is 2 out of 8. Notice that in general, I don't reduce, I don't simplify my fractions when dealing with probabilities, because 2 out of 8 is simpler to comprehend than 1/4 or whatever. So it's easier usually to figure out what's going on if you don't simplify things. Actual odds against. The actual odds against an event A occurring is the ratio, the probability of not A divided by the probability of A, and is usually expressed in the form A colon B, where A and B are integers having no common fractions. So actual odds in favor. The actual odds in favor of event A is the reciprocal of the actual odds against the event. We'll just take the reciprocal of this. The payoff odds. The payoff odds against event A represents the ratio of the net profit, if you win, to the amount bet. The payoff odds against event A is the net profit colon the amount bet. So let's do an example. If you bet $5 on the number 13 in a game of roulette, your probability of winning is 1 out of 38. So there are 38 things that you can win, 38 little slots that it can go into. And so it was 1 out of 38. So that's a probability of getting any of the ball falling into any of those slots is 1 out of 38. The payoff odds are given by the casino as 35-1. So they're going to make a little bit of money there in the long run. Find the actual odds against the outcome of 13. And so, how much net profit would you make if you win by betting on 13? So let's find first the actual odds against the outcome 13. So let's find the probability of getting, well, having the ball fall into the slot labeled 13. Well, there are 38 slots. So it's 1 out of 38. Well, they tell you here, it's 1 out of 38. What's the probability of not getting a 13? Well, everything else. So it's just being in any of the other 37 slots. So 37 out of 38. So the actual odds against are 37 over 38 divided by 1 over 38. So 37 over 1. So the actual odds against getting a 13, having the outcome of 13 is 37 to 1. The payoff odds are 35 to 1. So for every $1 bet, you have a $35 profit. So for a $5 bet, well, 5 times 35 is 175. So you have $175 in net profit. And so the bettor would get $175 plus their $5 bet back. So they would get their winnings would be to collect $180. You would have a net profit of $175 if you land on 13. Your winnings would be $180. They give you back $175 plus your $5 that you bet. Let's do an example. Flip a coin once. Find the probability of getting head. So let's look at this again. From now on, we're assuming equally likely cases. So the sample space, head, tail. Probability of head, well, there's 1 out of 2, so 1/2. The sample space S is the set of all possible simple events. Again, complement of E is the event that event E does not occur. The probability of the complement is 1 minus the probability of the event. So now, suppose you have 5 red balls and 7 blue balls in some box. So you have it in some box. What is the probability of randomly selecting a red ball? So you have some box with these 7 red balls with these 5 red balls and these 7 blue balls. You put them in this box and you just shake up the box, and then you stuff your hand into the box, and you're not able to see what the contents of the box are. You just feel around to find a ball, and you want to look, did I get a red ball? Did I get a blue ball? What's the probability of selecting a red ball? Well, there are a total of 5 red balls out of the total of 12 balls in total. So 5 out of the 12 balls are red. So the probability of selecting a red ball is 5 out of 12. So 5 over 12. Suppose you flip a coin 3 times. And so you flip a coin again, flip a coin again. So first time you flip, you get a head, second tail, third head, etc. So you get head, tail, head. What is the probability of getting no head? Okay, so let's figure that out. What's the probability of getting head first time? Okay, let's figure that out. So first, flip a coin, head, tail. Flip a coin second time, head, tail, head, tail. Flip a coin a third time, head, tail. Each time, doesn't matter what you just flip, it's going to be head, tail the next time. So, figure out the sample space. Head, 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 head. Start again. Head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. So this is your sample space. So, let's find one that has no head. Well, certainly that's got a head, that's a head. Oh, there's tails. So only this one has no head. Tail, tail, tail. So 1 out of the 8 has no head, has only tails. So this one only consists of tails. And so probability of no head is 1 out of 8. Let's find the probability of head first time. So 1, 2, 3, 4 have head the first time. Uh-oh, tail, first time, nope, don't want that. So 4 out of the 8 have head the first time. Suppose you roll a pair of dice. What's the probability that the sum is less than 2? There would be easier ways to figure that out, because this is a particularly trivial question. But let me show you how to do this problem in general. So let me do this in general. So first, you have one die. On a die, it has anywhere between 1 and 6 little dimples on each of its 6 sides. I'm assuming a regular pair of dice. So they're somewhere between 1 and 6 dimples on each of these dice. Then they say, figure out what the sum is. So let's add. So in this case, I'm not going to give you the sample space. Instead, I'm going to give you the output. So the output is the sum. And so 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3, 4. 1 plus 4, 5. 6, 7. 2 plus 1, 3. 2 plus 2, 4. 2 plus 3, 5. 6, 7, 8. 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11. 7, 8, 9, 10, 11, 12. So now, so you construct your, the outcomes. So again, these are the outcomes from your sample space. You can figure out what the sample space is. Say for the event, you roll a 5 and then a 4. Your event is, so your event is 5, 4, but the outcome is 9. So I just write down the 9, but you could construct from this the sample space. I just don't write it down. It's easier to figure out what, look at the outcomes and count them. So how many have a sum less than 2? None out of the 36 numbers here. So 0 out of 36. 1,010 adults were surveyed, and 202 of them were smokers. Find the probability that an American adult is a smoker. Find the probability that an American adult is not a smoker. So 202 out of the 1,010 were smokers. Everyone else was not a smoker. And so 1 minus, so it's a complement. So what's the complement of a smoker? So it's 1 minus the probability that they are a smoker. So 1,010 minus 202 is 808 over 1,010. That's the probability that they are not a smoker. An event is unlikely if its probability is very small, such as 0.05 or less. An event is unusually low. An event has an unusually low number of outcomes of a particular event, or an unusually high number of those events if it is very far from what we typically expect. And we're going to be using that, especially in hypothesis testing. Okay, so that's it.